How is everybody? Ready for Friday like me? Too many limits? You've reached your limit? You've reached your limit of limits? Infinity? We're about halfway through the semester, right? So we do have an exam coming up next week. So exam number 2, it goes up to 11.2. So 7.7 to 11.2, the sections will be covered. There are no centroid problems on the exam. Not all of the professors cover centroids, so they get to choose which of 3 sections they get to cover. So there will not be on there. I like centroids because they're extremely powerful and can help you on other things that are on the exam.
So we can use centroids in exam?
Yeah, you can use them. Right, but if they ask you to set up an integral on a word problem, you've got to set it up. So that's okay. Yes, hydrostatic force is. Yeah, everyone covers hydrostatic force. It is on the program. It is on the exam. So just centroids, that second part of 8.3 is not. So I put up some review materials. I emailed those out. So there's lots of. I think there's at least 6 old exams for you to work through. The review materials are a little short on 11.1 and 11.2, so sequences and series. So you might want to be working on doing extra homework problems from the book for those. So I did also put up exam 3 review materials because that does have some sequences and series stuff on it that you can use. So yes. Today is 11.2, and then on Monday we will cover more of 11.2. So, yeah. If we don't get to it today, I plan on getting to it today. If not, I'm going to send out a video. Okay. Yeah, we'll get to one. All right. You're welcome. All right, let's start with a prayer. Who would like to offer a prayer for us? Thanks.
Heavenly Father, thank you for this day, this opportunity we have to come into study calculus and we ask the blessing upon us and be able to have what we need to do all as we study and try our best. In the name of Jesus Christ.
Thank you. Do you work the BYU Creamery?
No, just free shirt.
Oh, free shirt. That was one of my jobs when I was an undergrad. I worked at the BYU Creamery. So, okay. So there's Eichlinger problem up here. You're working on. When you finish that, there's also a proof that 0 equals 1. So we'll try to figure out what's going on there. Yeah, my proof that 0 equals 1. Well, there isn't. There's no negative. Every negative 1 got added to 1. Yes. Oh, thank you, Mary. Yes. When I saw you come in, I thought of it, but kept talking about something else. Thank you, Mary. Okay. A couple conferences ago, Lynn G. Robbins, member of the presidency of the 70, gave a talk on repentance, and it's an awesome talk. If you don't remember it, I highly encourage you to go listen to it. And he actually shared a story about a professor that he had, a physics professor here at BYU, and he talked about how this professor would write. You could take exams as many times as you wanted. If you were not happy with your score, you could retake it. The teacher would rewrite a similar exam, and you could retake it, and then you could retake it again, etc. I'm not doing that in this class. Didn't mean to get your hopes up. But I do have a repentance policy, and that repentance policy is I will replace your lowest midterm score with your final score if your final score is better. So I know some of you did not do as well as you hoped on the first exam, and some of you might not do as well as hoped on the second exam. The third exam actually tends to be the hardest exam. So just FYI, yeah, study hard. But you can vary a bad test score that way in this class by doing well in the final. And of course, to do well in the final, you've got to know the material quite well. So study hard and learn the material. Yeah, if you want to take your lowest midterm score and replace your final score, then I can do that for you, Brian. Sure. No, we're not replacing your final score. So, okay, good question. Oh, I am recording. Thank you. Thanks for reminding me. Okay. What kind of, well, who needs more, snap if you need more time doing this problem. Okay, take 30 more seconds or so. Yep. You can talk to your neighbor about the proof, the 0 equals 1. Tell them your ideas you're having over there. There is no way. There's infinite. Yeah, I can.
0 equals a quantity that equals 0.
No, 0 equals 1. If 0 equals 1 plus a bunch of zeros, aren't you okay with this? Aren't you? You're not okay with this step?
I'm okay with the top one.
Okay, well then you got to be okay with this one. It's just 1 plus 0. Are you okay with 1 plus 0? If you're okay with this one, then yeah. Yeah, it is. That's what I said. 1 plus, all these zeros are 0. You agreed with that. So this is 1 plus 0. And just 1. That's what I said.
But 0 doesn't use 1.
I just proved it does. No, I used infinitely many ones on all of these except for this one. I'm not. I don't cut off anything. It's infinite. I don't ever stop. There isn't one negative 1 that isn't matched up with a positive 1.
Right. Just have 0 equaling 0.
All right. Okay, I'm going to end this. Okay. So what kind of series is this? What kind of series is this? Geometric series. Okay. A geometric series is of the form okay. It's of this form. Actually, before we do this problem, I meant to tell you guys a story. I was watching a TV one day. I was kind of a documentary about the moon landing, and they casually threw in a fact that scared me to death. They said that when they actually landed on the moon, there's part of the rocket that they were in that actually shoots back up to 2 astronauts, and they meet with the other one that's circling the moon, and they connect back together. Well, when they go to launch off that lunar module up to meet with the orbiting craft, they said that for every pound that lunar module weighs, and any pound of anything on it, it takes 2 pounds of fuel to get it off the moon. Now, why should that scare any astronaut to death? Okay, so someone said it's going to take infinite amount of fuel. The fuel's part of the weight of the thing. Oh, yeah. Yeah. Or what if they got, so the context was they were bringing things back to put on the shuttle. They were collecting things from the moon to bring back to Earth. And if they brought back 1 pound too much, there would have been 2 pounds low on fuel and not make it back. So they had to be super careful. But still, there's a problem, because if you've got 100, we'll just say 100 pounds, I'm sure it's more than that, 100 pounds of stuff to bring up, It takes how much fuel? 200. But now you have just added 200 pounds of stuff. So now you've got to add on another 400 pounds of fuel. And you can't, you'll never get that thing off the moon. Okay, so she said maybe that fuel includes carrying itself. Okay, then how would you figure out how much fuel you would need?
So we talked about the mass or the weight, because things are lighter.
Yeah, so this was what it would weigh on Earth. So, but, that's true. If you need 2 pounds, or there might be some way to think about it. But okay. So actually what they had done, they had already done some math and realized that there was actually some amount that was less than 1 pound needed to get 1 pound of stuff off the Earth. Some amount of fuel, off the moon. Some amount of fuel to get 1 pound off. But then you needed to add another amount to get that small amount off, and then another amount. So whatever weight you had, you had to multiply that weight by some number, and that weight by that number times that number, and that weight times that number squared. So they'd actually already done the math where, okay, maybe it didn't take 2 pounds. The very first time to get that 1 pound off, you would need like 2/3 of a pound, or 3/4 of a pound, or 1/3 of a pound, and then you could get it off. But then you need to figure out if it took a third, you need 1/3 of that 1/3 of a pound more fuel, and then 1/3 of that 1/3 of that 1/3 of that pound too. Fuel. Oh, so this is already, that's another calculus problem. It's because, of course, as soon as you start to burn fuel, it gets lighter. That's differential equations actually. So, yeah, that's already taken into account on that very first piece. Okay, and this looks a lot like the problem we just had. So that 2 pounds was after they had done the math. It already included all those little pieces they had up to get the piece off before. So, oops, wrong one. Okay, so this is a geometric series. A geometric series here, let me copy this down here. Oh, I missed a piece. Let me just rewrite it. 2 So notice, to get each number, we multiply it by the same thing. We multiply the previous term by the same value, etc. So this same value that we multiply is called the common ratio. Oops, common ratio. Okay? And if you have an infinite series, an infinite geometric series, you can actually figure out what that sum is. The book does this. I'll run through it really fast. Okay. So actually, we won't make it infinite yet. We'll call this AR to the n. So I'm going to multiply everything by r. So here I have SR. Here I have AR. AR squared, AR cubed, to AR n plus 1. Since I multiplied it by r, the powers will go up by 1, and then I just kind of line them up. And now what I'm going to do is I'm going to subtract that lower one from the upper one. And here I get S minus SR. And this is going to allow a bunch of things to cancel out, because as I distribute this out, those cancel out, etc.
And all I end up with is a minus ar to the n plus 1. And if I divide, here I can pull out an s. And then I can divide by n minus 1. Sorry, I can divide by 1 and minus r. Okay, so you do that algebra, and I get that expression, and I have to really think about what's happening to this expression right here, to this term. Oh, did I write in minus 1? Yes, it should be plus 1. No wonder there's a problem there. Okay, what's going to happen to that term if r is larger than 1? Or larger than 1 in absolute value? It'll diverge. You just keep getting something bigger and bigger and bigger and bigger and bigger. Or if it's a really large negative number, it won't converge at all. You'll just get a large negative, then you multiply it by that large negative number, and then you get a larger positive, and then a larger negative, and then a positive. But what happens if that r is less than 1 in absolute value? Yeah, if you keep multiplying something by a number less than 1, that something's going to get closer and closer and closer to 0. So in the limit, as n goes to infinity, that goes to 0, and I end up with a over 1 minus r as the sums, where a is my first term. It's the easiest way to think about it. You take the first term and you divide it by 1 minus your common ratio. So then we can just apply that in this case. Our first term was 2. Our common ratio was 1 minus, it's a negative 1/3. So you end up with 2 over 1 plus 1/3, which is 2 over 4/3, which is 6/4, which is 3/2, which was C. So good job. So okay. Now, yes, questions? Yeah, so the S is the sum. We're trying to figure out if we add up all of this, what is that going to be? And I'm going to call it S. So my goal is to figure out what is S, or what is a formula for S. So I want that sum to be, like if I have a geometric series, and this is a general series, geometric series, then what should that sum be? So I just called whatever that sum is S. Thanks. Okay. All right. We good? Tana? No, so what they were thinking was if you had, they were giving me the total sum, and they had already calculated a sum. So if they had like 1 pound, they needed some weight, or a ratio of that weight, plus the ratio squared of that weight, plus the ratio cubed, because they multiplied by r. To get that first pound off, they needed to get like 1/3 or 1/4 or 2/3 or 3/4 pound to get that 1 pound off. But then to get that 2/3 or whatever pound off, that first r, you had to get the next one. You had to get 2/3 of 2/3, and then to get that 2/3 of 2/3, you had to get 2/3 of 2/3 of 2/3 pounds of fuel to get it off. And so then you had to add all that up, and after they added all that up, they got 2. That was how they got the 2. Was it actually takes less fuel. If the fuel didn't weigh anything, then it would take. Well, then of course it takes 0 pounds of fuel to get it off, but 0 equals 1, so it would take 1 pound of fuel. All right, okay. Yeah.
At the bottom of that other page, where you have the A minus AR, I was wondering, I didn't catch, why did it go to 0? That one part of it?
So if R is less than 1 in absolute value, then then R to the n goes to 0. Right? If as n goes to infinity. Right? If you think of a half times 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 a half, right? 90% of 90% of 90% of 90% of 90%. It can even be negative, like a negative 1/2 times a negative 1/2 times a negative 1/2 times a negative 1/2. You're still going to get close to 0.
So if it's R greater than 1, then you can't do that.
That's right. That's why this formula only works if R is, that common ratio has to be less than 1 in absolute value. So, thanks. Thanks for helping to make that clear. Yeah, it was 2 divided by 4/3. Okay, so here's a few series, and my question is, okay, here's several series. My question is, take a minute, look at these, try to decide first if they converge or diverge, and why. And if they converge, you can figure out what they converge to. And if you don't know one, that's okay. A lot of these, some of these you'll know, some of these you won't know. Okay? But the goal is to start thinking about what tools could we start to bring to think about whether a series converges. You're welcome to talk to your neighbor about these. So take a few minutes. Okay. So I know a lot of you have questions about what you've read, and a purpose of doing this is to help answer those questions. So give us context to talk about a lot of the language and the theorems and stuff in this section. So I should add a series. I know you guys read this, but a series is a sum of a sequence. You take a bunch of terms and you start adding up those terms of a sequence. And it's much harder to figure out if a series converges rather than a sequence converges. In the same way that it's a lot easier to find a derivative than it is an antiderivative. Same thing. It's hard to know whether the series converges and diverges. And if it does converge, it's really hard in most cases to figure out what it converges to. Geometric series is a nice example, but all series are not geometric. All right, what are we thinking about this first? About number 1 here. Diverges. Why does it diverge? Yeah, we keep adding larger and larger values. If you give me any number, I can go out far enough and get a number larger than that. So it's going to go to infinity. Okay? So this diverges. So this infinity or diverges. Okay. What about the next one? Okay, so this is a geometric series. So it does converge. This is actually a good time to talk about what do we mean when we say a series converges? How do we even talk about a sum of infinitely many things? You guys were having trouble talking about the sum of infinitely many things up here, right? Up here we had things like this. There's a sum of infinitely many things, or here's a sum of infinitely many things. And you're like, but that last one, well, there is no last one. It's infinite. But we should have some way to think about what the sum of infinitely many things is. And the way we're going to do that is we're going to think about, we're going to create a new sequence. We're going to take the series and create a sequence. And then we're going to create that sequence, a sequence called the sequence of partial sums. So here we had 1 plus a half plus a fourth plus an eighth plus a 16th, etc. Here, maybe we'll start with the easier one. 0 plus 0 plus 0 plus 0 plus 0 plus 0. Okay, so some people will just say, oh yeah, that's 0. But some of you might still be uncomfortable saying that's 0. So snap if you are uncomfortable saying that's 0. Okay? So I've had students in my last class, someone student was very uncomfortable saying that this would be 0. So, and even more uncomfortable saying that this equaled, what do you guys say this equals? 2. And even more uncomfortable saying that should equal 2. Because you never quite get to 2, right? I mean, you can go way, 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 way out there and you're still not equal to 2. Like, it's not really 2. So this is how we're going to define a sum of an infinite series. So the sum of an infinite series is the limit of the sequence of partial sums. So we're going to create a new sequence from this series. Here we've got a series right here, and what I'm going to do is start looking at the first term. and then the sum of the first two terms, and the sum of the first three terms, and the sum of the first four terms, etc. Those we call those S1, S2, S3, S4. Okay, so I'm going to create. So this equals 0. This equals 0. This equals 0. Any finite sum of zeros is going to be 0, right? So Sn is going to be 0, 0, 0, 0, up to n zeros. And the infinite sequence is going to be 0, comma 0. Didn't catch that. 0, comma 0, comma 0, comma 0, etc. This is now the sequence of partial sums. Okay? And what is the limit of that sequence? 0. The limit of that sequence of partial sums is 0. So the sum is 0. Okay? So that's why we would say that this side over here does actually equal 0, because if you keep adding up 2 and then 3 and then 4 and then 5 and then 6 terms and look at where those sums go to as you create a sequence of those things, it goes to 0. Here, that's kind of maybe a more obvious case, but let's do this side over here. Let's rewrite. I'm going to start writing out the sequence of partial sums. So S1 is 1, S2 is 1 plus a half, S3 is 1 plus a half plus a fourth, so I get 1, 3 halves, 7 eighths, sorry, 7 fourths, thanks, 15 eighths, and then I'd end up with 31 sixteenths, and then 63 64ths. Oops, no, I jumped ahead too much. 63 32nds, etc. What would I end up with? I would end up with, the denominator would be 2 to the n. The numerator is 2 times the denominator minus 1. Okay? So my new sequence of partial sums is 1, 3 halves, 7 fourths, 15 eighths, 2 to the n minus 1 over 2 to the n. Okay? That's the sequence of partial sums. So I had a sequence to begin with. That sequence was just 1, a half, a fourth, an eighth, etc. This was a sequence. And then I had a series, which was 1 plus a half, plus a fourth, plus an eighth. So that's the series. And then I created a new sequence, the sequence of partial sums. Okay? And what's the limit of those partial sums? What do these numbers keep getting closer to? 2. And we can actually do the algebra over here. Yeah, I'm going to take it down here. We can do the algebra. If you rewrite it as this, then in the limit, that goes to 0. Those divide out, you just end up with your 2. Okay? So the limit of this sum, this infinite sum, is 2 because the sequence of partial sums, the limit of the sequence of partial sums is 2. If the sequence of partial sums doesn't have a limit, then this sum is divergent. So for an infinite series to have a sum, that sequence of partial sums has to have a limit, has to have a finite limit. So, and whatever that limit is, that's what we're going to say is the sum. Okay, with that in mind, we're going to go back to this problem up here. Now, analyze that and you tell me what's wrong with this proof. You should have tools now to think about that problem. All right. So the groups I stopped at, we're looking at this line here, and they started to write down the sequence of partial sums. Oh, thanks, Emily. I'll save my voice. So let's start writing down the sequence of partial sums at this line. So 1 minus 1, 1 minus 1 plus 1, 1 minus 1 plus 1 minus 1. So this is going to be, this sum is 1, this sum is 0, this sum is 0. So what is that sequence going to look like? Yeah, you're just going to have a sequence of 1, 0, 1, 0, 1, which diverges, right? It doesn't get close and stay close to a number. So what do we know about this right here? Well, one thing we don't know, it's not equal to 0. So once I start taking off these parentheses here, I can take off any finite amount of parentheses and I'm fine. But once I say I've taken out all of them, it's not the same. This is not the same as the line above it. So, okay. So that's the power of thinking with the sequence of partial sums. All right. So this was, so this was 2. All right. How about this one? Number 3. So I heard you guys talking about it before. Why do you say it diverges? Yeah.
So one of the things that we said is if the limit as a addition is not equal to 0, then the divergence is
Why would it say that?
because I don't know if you think about with the limit, if it's above 0 as you go to thing, you're going to keep adding whatever quantity there is.
Right, but why are you thinking area under curve or adding just not numbers? Interesting. You can think about these as areas, and even an area on a graph where you just multiply the base by 1 and put a bunch of rectangles. So these are the heights of the rectangle. We'll use that in a couple of days. All right. So what do you think about this is what's the sequence of terms get close to here? If I don't worry about adding these up, and I just look at as I go out here further and further, what are the numbers that I'm adding up get close to? Not the sum, but just the terms themselves. 1/2. Well, if I keep adding up a half, or the half, or the half, or the half, am I going to get to some finite value? No. So to have any chance of going to adding up to some finite amount, the terms I'm adding up, they have to get close to 0. Okay? They have to. All right, so we've already talked about this next one, number 4, because that's the one that was the one in the proof. All right, how about number 5? So how about this one? Converge or diverge? So where are the terms going? To 0. So if the terms don't go to 0, it diverges. If the terms go to 0, then you don't know anything. Okay? I don't know how many times you have to say this. I don't know if you miss this on the exam, I'm going to tattoo it to your forehead. You know, it's a temporary tattoo that will wear off in 20 years. So there are series. If that's all we need to know about series, if that was true, this would be 1 day's worth, and we could do what? There are series where the terms are going to 0, but the sum is still infinite. Is this one of those? Some say yes, some say no. Here, let's do a quick eye-clicker quiz. Oh, we don't have time for an eye-clicker quiz. All right. Okay, this is a very special series. It has a name. You may have read about it in the book. You actually said no, because we talked about this in the reading. This is called the harmonic series. Okay? This is a harmonic series. So the harmonic series diverges. That sum is infinity. And why? We'll talk about it next time. Okay? I have a nice proof. We'll have a couple proofs for why it diverges. We'll talk about it next time. This is the alternating harmonic series. Down here, every other term is negative. Any idea what the sum of that is? It actually converges. Well, do the terms go to 0? Yep, the terms go to 0, so it converges. Right? No, you can't use that argument. Okay? The terms go to 0, but it means, hey, we still don't know anything. Okay? You know, absolutely nothing. Okay? Terms go to 0. Well, we know it doesn't diverge, but we don't know it doesn't. We're not sure yet that it diverges. So, what? You're just going to write "you don't know" on the exam? Well, we're going to spend the next 3 weeks figuring out how to know. So, okay, this does converge. Anyone know what this sum is here? Anyone got a guess? It's the natural log of 2, actually. Yeah. All right. Up here, number 7. Oops. I don't know what I hit. Oh no! Dang.
Oh wow.
Stop. Control Z. Okay. All right, here's another sum. The terms go to 0. Right? The numerator's already always 1. The denominators are getting larger and larger. So the terms go to 0, so we don't know. We don't know. We have to do something more. In this case, it does converge. Okay. So we're going to go through all of these. By the end of chapter 11, we'll know how to do all of these. And what their sum is, except for one. So this converges to pi fourths. Okay. The next one, the sum of the square numbers, 1 over the square numbers. Pi squared over 6. That's the one that's hard, that we won't get to in this class. Okay? Oh, I made a mistake on this one. This one is just a geometric series. So that's 1/3, but there's a really cool proof on why it's 1/3. We'll have to do another time. All right, how about 1 over the factorial numbers? And 0 factorial is 1, okay, by the way. So you guys may not have learned that, but 0 factorial is not 0, it's 1. Okay, we can talk about that another time. Okay, so it's actually 1, first term is 1, then 1, then a half plus a 6. Do you know what that adds up to? What did someone say? Said probably what? Probably infinity. It's actually E. Okay. Of course. Well, you're laughing about that now, but in 4 or 5 weeks you'll be like, oh, of course that's E. So, how about 1 over the square root of the whole number? The terms go to 0, so we don't know anything. Terms go to 0, and this diverges. So, yep, that diverges. So, and this last one, it equals 1. All right, so this last one is one they tell you how to actually do in this section. So in the last couple minutes here, I'll show you how to do this one. Okay. If you see a series that looks like you can do partial fractions, you can easily write it as the sum or the two things. So then you can actually do. Sometimes it will telescope. So 1 over n times n plus 1. If you do partial fractions, if you do partial fraction decomposition, you end up with a equals 1 and b equals a negative 1 in this case. So you can rewrite this as the sum of 1 over n minus 1 over n plus 1. Well, how does that help us? Well, I'm just going to start writing out the terms. Okay? This is a good strategy. Sometimes when the book or the test writes it out in this summation form, sometimes it's hard to get your head around it. Well, start writing it out like that. Just starting right out the first few terms. That might help you to get your head around it. Okay? So I'm going to start writing this out. At n equals 1, I get 1 minus a half. And then at n equals 2, I get a half minus a third. And then at n equals 3, I get a third. A third minus a fourth, and then a fourth minus a fifth. And what happens? Look, these add to 0. And importantly, what happens to that last term? It goes to 0. If it doesn't, if that last term keeps getting larger and larger and larger, then it'll diverge. But in this case, that last term goes to 0. You're going to end up with a 1 over n plus 1, and then goes to infinity. That term goes to 0. So what's the total sum going to be? Just 1. So there you go. Have a great day. Amaze your friends with these infinite sums.
So, how can I know, like, how do I know what I don't know?
I've asked for the rubrics. They haven't sent them to me yet. But you can also come in and I can sit down and go through with you.
Okay,
and
because
try
I don't want to
figure
take
it
your whole office hour, though, just, me complaining about the exam.
out. What did you get on the exam?
Not very well.
Not very well.
Well, so let me put it this way. There's about 30% of the stuff that I don't know, and I want to make sure that I know that 30%.
Here, hold on. Let me stop this before we...
Then people will actually want to do